There are a lot of ways you can describe how materials interact with magnetic fields. Most materials can be described as either diamagnetic, paramagnetic, or ferromagnetic. Please note that this list is not exhaustive. There are, among other things, ferrimagnetic, superdiamagnetic, superparamagnetic, and a bunch of others which, if you really want to know, go ahead and check Wikipedia. But these are the most common for everyday materials. And all of these are governed by quantum mechanics, so things will get a little weird. So let's start with diamagnetism. Now, in the last lecture, I said that electrons, despite spinning and orbiting the atom, aren't actually moving. Well, that's not entirely the case. You see, if you apply a magnetic field to an atom, and specifically to the electrons in the atom, they will experience something similar to Faraday's law. Recall that Faraday's law says that a changing magnetic flux will cause an electromotive force that will cause a current going in a particular direction. Well, in this version, the changing magnetic flux, which you get from bringing the magnet close to the atom, will create an instability in that atom, a kind of wobbling to that atom, with the net effect that the electron will tend to move in a circular pattern. This pattern will act like current going through a loop, will create a magnetic field, and like other applications of Faraday's law, in particular Lenz's law, that magnetic field that electron wobble produces will oppose the applied magnetic field. Now, this is something that happens with all atoms, with everything. However, it tends to be really weak. So diamagnetism tends to be the if you have nothing else type magnetization. Now, materials that are diamagnetic will tend to try to push away from magnetic fields. So this will behave the opposite of what you're used to, for instance, magnets. You take a refrigerator magnet, hold it near your refrigerator, and the refrigerator and the refrigerator magnet attract each other. Well, if the refrigerator were made of a diamagnetic material, then the refrigerator would actually push away from the magnet. This is usually very, very weak, a very, very weak effect. However, if you have a really, really strong magnetic field and a relatively strong diamagnet, you can get some weird results. I will link on Canvas a video of a frog being levitated in a super powerful magnetic field. It's a 10 Tesla magnetic field, and it turns out frogs are almost entirely water, and water is a pretty diamagnetic material. Now, this isn't quite diamagnetism, but superconductors. These are materials that will allow electrons to flow through them without stopping the electrons at all. In a superconductor, the electrons are not bound to the atom, so this isn't actually diamagnetism. However, because the electrons are allowed to freely roam around, they will be affected by Faraday's law. And as a result, when you try to put a magnet close to a superconductor, the electrons will start creating these macroscopic eddies, which will have the effect of creating a magnetic field to completely oppose whatever magnetic field you were trying to apply to it. The net effect, superconductors will always have exactly zero magnetic field inside of them, and they will push against any magnet that tries to get near them. All right, so that was diamagnetism. The next one is paramagnetism. So for diamagnetism, just the mere existence of electrons apply a magnetic field to them and they start to oscillate. Well, paramagnetism relies on the inherent magnetic fields that the electrons themselves have. That relies on the magnetic field from our previous lecture. If you put a magnet, if you put a permanent magnet, like a bar magnet, inside a magnetic field, that bar magnet will try to line up with the ambient magnetic field. Same thing happens with these atoms. The electrons will change the direction of their spin to line up with the external magnetic field. And unlike paramagnetism, this will actually cause the applied magnetic field to increase. So for instance, you put a 1 Tesla magnetic field inside into a paramagnetic material, and you actually get a 1.01 Tesla magnetic field. I should point out that these effects are usually not extremely strong, but they are there and they can be measured. And I'm pointing that out because the next one, ferromagnetism, is strong, or rather it can be. So one way to think of ferromagnetism is it's kind of an extreme version of paramagnetism, plus a little extra quantum weirdness. So like paramagnetism, ferromagnetism relies on having these unpaired electrons, these electrons that can have any orientation they want. However, ferromagnetic atoms have an additional property that comes from this thing called the Pauli exclusion principle. The Pauli exclusion principle is why you can't have all of your electrons in an atom in the ground state. You know, you can only have 2 in the first level, 8 in the second level, and so on. And that's because no 2 electrons can have exactly the same state. So that you can have 2 in the lowest energy shell because you can have a spin up and spin down. You can have 8 in the next shell because you can have two in the S, 1 spin up, 1 spin down, and 2 in each of the P subshells, which 0, +1, and -1. So 2 of each of these, so that's 6, plus another 2, 8. You can have 8 in the next shell. Anyway, another property of the Pauli exclusion principle is that if you have, say, 2 iron atoms, and I'm going to use iron because it's the most well-known ferromagnetic material, but if you have 2 iron atoms and they are in a crystal lattice, then the Pauli exclusion principle says that two unpaired electrons, one from each atom, will have to be farther apart if they are in the same spin direction, and closer together if they're in the opposite spin direction. Well, electrons will still do exhibit a repulsion towards each other. They're both negatively charged. They both try to repel each other. So they both want to be in the state that's farther away, which means that they both want to be lined up spin-wise. Now, iron exists in a crystalline form, which means that each iron is bound to a bunch of other iron nearby, and a bunch of those irons are bound to a bunch of other irons nearby, and so on and so on. And if every iron wants to be in the same spin direction as its neighbors, then you could, in theory, have every iron atom in that piece of iron having spin in the same direction. Now, it doesn't quite work that way because iron is not a perfect crystal. There are going to be what are called domains. Within the domain, yes, all the unpaired electrons are aligned in the same direction. However, what you tend to happen is one domain over here starts forming in one direction, but a domain nearby starts forming in a different direction. And those domains will grow as the electrons try to line up. But then when the two domains meet, they can't line up because the one domain is already established, the other domain is already established, and it would take a lot more effort to change the direction of the domains than they can actually exert on each other. Now, one exception to this, as I mentioned in Tuesday's lecture, is if there is already a strong applied magnetic field to the iron, when it is first forming these domains, all of the domains will start off pointing in the same direction. And so you will get a strong magnetization in that material.